Hi everyone, today we're going to be looking at solving more trigonometric identities and other stuff related to trigonometry. So our first question is sine 3x over sine x minus cos 3x over cos x. So as I explained in a different video, the one before this and other stuff before this, is that when we have 3x, we can virtually do nothing with it. So when we see a 3x in a trigonometric function, what we would usually want to do is split it up as sine 3x equals sine 2x plus x, which, as you know, is the exact same thing as we just 3x or 2x plus x. But what this form allows us to do is that we can now write, well, we know that alpha plus sine alpha plus beta equals sine alpha cosine beta plus sine beta cosine alpha, right? And so this is the same thing. So then we can split up sine 2x plus x as this rule over here, right? So let's do that and write sine 2x would give us then, well, actually let's write it out. Sine 2x plus x over sine x. The denominators we keep the same, we don't change them since we can do virtually nothing with them right now. Cos 2x plus x, we do the same thing as sine x, we split it up. Cos x here. And so let's open this whole thing up and we write it as sine 2x cos x, sine x, cos x, sorry, cos x, right? Plus minus, and we do the same thing here, but there's a different rule for cosine. Now I'll write it up just in case. Minus, that's a very important point, that for cosines it's a negative, it's the opposite sign of whichever is in the bracket. So cosine alpha cosine beta minus sine alpha sine beta. So let's try that out. Over cosine x. Now from here on out, it doesn't really look too beautiful, and we can't really simplify this as much as we want to. So we have to realize that we have 2x, 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 and 2x. Now the single x's, so wait, these ones we can do nothing with, right? Since they're just x's. So there's nothing we can do about them. But what we can do with is those 2x's. Now, since we want to simplify this equation, that means we have to get rid of something. But how do we get rid of something? Well, in trigonometry, it could mean having a sine squared x plus cosine squared x, because that would give us 1. Or it would mean dividing by sine x on both the numerator and denominator, since if we have a sine x here, we can just simplify with the denominator, and we have a cosine here, we can just also simplify it with the denominator. So in the first fraction, our goal is to get sine x in the numerator. So how do we do that? Well, first of all, we have a sine x here, so we have to somehow get a sine x here. What do we have on this side? Well, we have 2x, sine 2x. Let's open it, see what happens, right? 2 sine x cosine x plus sine x cosine 2x. Now, before I continue, as we can see, we have a sine x, and a sine x. Right, so this already simplifies away. So if we can do this here, we can most likely do it on the other side as well. So let's do that. We have to get cosine x on this side, right? We have a cosine x in this multiple, so we have to get it also on this side. So it's cos 2x cos x minus, and we do the same thing we did here when opening the sine 2x. So we get 2 sine x cos x sine x, because there's one more here. divided all by cos x. So let's take it out and divide it by sine x. So sine x times 2 cos x plus cos 2x over sine x minus, and we do the same thing here but with cosine x cos 2x minus 2 sine squared x, since we have two more sines, divided by cosine of x. Now cosine cancels out, and sine also cancel out. So we're left with 2 cos x plus cos 2x minus cos 2x plus 2 sine squared x. Now with this we can just already simplify and subtract cos 2x and cos 2x. We get 0 there. So we're left with 2 cosine of x plus 2 sine squared x. We can further simplify this and get 1 minus cos squared x from sine squared x, but that would be pretty much pointless. So we're done, and we're left with this little expression. So that is how we simplified sine 3x or sine x minus cos 3x or cos x into 2 cos x plus 2 sine squared x. Another example we can look at is cos a, let's say use a, plus sine a over cos a minus sine a, and all that equals sec 2a plus tan 2a. So we have to prove this identity over this equation. So the left side looks like nothing can be done, and the right side just looks plain ugly with the sec and tangent. So let's keep the left side, and even though we usually don't touch one of the sides and we just work on only one side in IB, let's look at the right side and not really touch it, but more of just explore how we can look at it differently. So sec 2a is 1 over cosine of 2a plus sine of 2a over cosine of 2a. Okay, so we didn't change, right, anything. Sec 2a we wrote it as cosine, and tan we just opened it as sine over cosine. And as we can see, we have the exactly same denominator on the left and right? So then let's have that and write it as 1 plus sine 2a over cos 2a. Okay, and now let's look on the left side. So the left side, cos plus sine and cos minus sine. What rule do we know that we can have this turn into a quadratic, a difference between two squares, right? Well, we can multiply by the positive of the denominator, both top and bottom, to get the square of this expression. So let's do that. So we'll get cos a plus sine a squared all over squared a minus sine. Now you would ask, why did I decide to do this exactly and not something else? Well, the reason because there is nothing else that you can do in order to make this work. Because what else could you do? You could square the whole fraction, but that wouldn't really work because you would just get the same thing but squared. So one of the only things you can do here is what I just did, which is multiply by the positive of the denominator in order to, let's say, rationalize it. But you don't really rationalize it, you just square it. Now we get cos squared a minus sine squared a, but that is an identity. So cos 2a equals cos squared a minus sine squared a. It also equals other things, but that is one of the things that cos 2a equals. And as we can see, that is exactly what we have in the denominator here. So let's simplify it and write it as, well, let's open the numerator as well. So it will be cos squared a. We just obey normal rules of opening a quadratic fraction. So it will be cos squared a plus 2 sine a cos a plus sine squared a over cos 2a equals 1 sine 2a over cos 2a. Okay, so we already have the same denominator. Fine. But the numerator on the left side looks very, very ugly. So, and it looks like there's nothing we could do with it. But what if I told you we can just rewrite it and you would get exactly what we have to do with it? So let's just rewrite the same thing as sine squared a plus cos squared a plus 2 sine a cos a I accidentally wrote a Roman numeral. Okay, so now in this form we can actually see that this is our basic trigonometric identity and this equals to 1. And so that looks very, very better, so much better, because now we just rewrite it as 1 plus 2 sine a cos a divided by cos 2a gives us 1 plus sine 2a over cos 2a. But still this equation doesn't make sense. So what we would want to do is, if you see the 2 sine a cos a, we can rewrite that as 2, well, we can't rewrite it, but there's an identity, which is sine of 2a gives us 2 sine a cos a, right? And as we see, that is exactly what we have on this side over there. This is exactly what we have here. So let's rewrite it as 1 plus, as 1 plus sine 2a over cos 2a and as you can see, we have proven the identity and this equation as the left hand side equals the right hand side. And that is how you prove that the very top cos a plus sine a equals over cos a minus sine a equals sec 2a plus tan 2a.